right, everybody, we are in for a treat. We got a ton of formulas we're going over for our memorization test. I've got a lot of stuff that's going to be fill in the blank, so I did my best to kind of set that up. Some of them might be fill in the blank on the test, but they're not on here, and I'll kind of talk about that in a minute. So even functions, all right? We have to know that f of negative x is equal to, fill in the blank, f of x. Oops, f of x. The negative disappears, in other words. The negative that's with x goes away. Even functions, we also have to know the type of symmetry. They are symmetric about the y-axis. Y-axis. To help myself remember this, I know that an even example of an even function is y equals x squared because it's got an even exponent. And I know that its graph looks like this. Right? The symmetry is about the y-axis. So all even functions are symmetric about the y-axis. Odd functions, if we start with f of negative x, this one is going to be equal to negative f of x. Which means if we change the coordinate of the sign of the x coordinate, it changes the sign on the y coordinate as well. All right, and so these are going to have symmetry about the origin, or you could say rotational symmetry. The way I remember this is I think of y equals x cubed, because that has an odd exponent, and it is symmetric about the origin, like that. All right, so odd function, I also know O and O, odd functions are symmetric about the origin. All right, arithmetic sequences and geometric sequences. There were two formulas here for both of these. I'm just going to have you guys memorize these. So this is for a general term. For any term, I'm not using the zeroth term like some of these do. I'm using what's called the kth term. Okay, and so this is our formula for an arithmetic sequence. This is our formula for a geometric sequence right here. All right, transformations. I will be gracious with your spelling, but there's going to be a lot of fill in the blanks for A, B, C, and D and what they do to a graph. Okay, and so we have to know that that it's called a vertical dilation, and that B is a horizontal dilation. All right, so A is a vertical dilation, B is a horizontal dilation. And A is going to multiply, it's outside, so it's going to multiply the y coordinates by whatever A is. Okay, so again, A is a vertical dilation, it multiplies y by whatever A is. B is going to multiply, it's on the inside, so it's going to affect x. Okay, it's going to multiply x, but it multiplies it by the reciprocal of B, 1 over B. C is on the inside. Anything on the inside is horizontal. Okay, so C is going to be a horizontal. We're going to call it a translation or shift. I would accept either translation or shift. And it moves the graph left or right. Left or right, whatever C is. D is on the outside, so it is a vertical translation or shift, and it moves the graph up or down. All right, so not too bad, just the vocabulary is going to be probably the toughest part to remember there. We have not used this formula in a while, so this is the formula that's used to calculate arc length, or the angle measure in radians, or the radians. Okay, and so I could make you guys write down this formula by asking for the arc length formula, or I could give you the formula and ask, okay, what does theta represent? Well, it's an angle in radians. What does S represent? It's the arc length. What does R represent? It's the radius. So radian, radius. All right, moving into right triangles. So there's a few things we could write here, but it's not a unit circle question yet. Okay, so you either need to write the definition of sine, which is opposite, over hypotenuse, Or I would also accept, we talked about this being the y coordinate over the radius, right? Both of those are fine here. Opposite over hypotenuse or y over r. Same with cosine. You could remember this is the adjacent over the hypotenuse, or you call it x over r. And the tangent is opposite over adjacent, or y over x. That's the same on the unit circle as it is with the normal right triangle. And that brings us to our unit circle trig ratios. And so same thing, but now we're going to apply them to the unit circle. So we have to know that sine of theta is y, and cosine of theta is x. And that tangent of theta is y over x. I don't know if this is helpful or not, but somebody years ago was having trouble or having a difficult time remembering which one was y over x and x over y. And so they just said terrible yearly x-rays. And so that kind of stuck with me. You do not, obviously, if you already have that down, don't worry about it, but terrible yearly x-rays. And then that helps them also remember that cotangent is the reciprocal x over y. X over y. Now, if it's a unit circle question, we either have to know that cosecant is the reciprocal of sine, or I would also accept 1 over y because sine is equal to y. And then secant is the reciprocal of cosine. And I believe the way many of you remember this is that you remember that secant and cosine are almost the same forwards and backwards. Or if you just flipped it, right? Cosine would almost spell secant if you change the O to an E. All right. Inverse trig restriction. So we've got our 3 inverse trig functions here. The inside could be called anything. I called it x. Doesn't have to be x, though. But you guys need to know what the restrictions are for these 3. Okay? Inverse sine is the right half of the unit circle, and so it's negative pi over 2 to pi over 2, included both of those. Inverse tangent is going to be negative pi over 2 to pi over 2, but not included. And then inverse cosine is going to go from 0 to pi. 0 to pi. All right, if you want to include all these, it's fine. It really is not a big deal if you know this one is excluded. So I would also accept if you included all of these here. All right, logs and exponents. It's been a little bit since we've done this. So we're just going to convert very basic questions. They'll have letters. There won't be any numbers in the question here. But writing a log in exponential form, you either have to memorize the formula for it, or what I do, or what I taught you guys to do, is just move the a over here, so the log is on the left, delete the word log, and switch the other 2 things here. So in other words, where the b is going to stay, it's still the base, okay? And then the a and the c are going to switch, and the a jumps up into the exponent, the c jumps across the equal sign. And we got rid of the word log, and so this would be our answer here. Writing that log in exponential form. This is going the opposite direction, so it helps, again, if the exponent is on the left. The base is always the base, so the bottom of the log is the bottom of the exponent. So I'm going to write log first. B is still the base, and the other 2 things switch places. So C goes here, A goes there. Writing a log, or the sum or difference of logs as a single log, all we have to remember is whenever we're adding logs, we multiply the insides, and whenever we're subtracting logs, we divide. And so this would become log base b. We're going to have just that one log here. There's going to be a fraction. We're going to multiply a with c, and then we're going to divide by d, like this. All right, again, I'm multiplying a and c because I was adding their logs, and I am dividing by d because I was subtracting its log here. The last thing is just rewriting this, not in exponential form, just rewriting it in another way. Anytime you have a number out front, that number is allowed to jump up into the exponent right here, like this. Okay, and oftentimes what happens on questions for later on down the road is this property gets combined with this one here. All right, Pythagorean identities are going to be fill in the blank. I meant to put this as a 1. It's supposed to be a 1 here. So you got blank plus blank equals 1, 1 plus blank equals blank, and then I've got the 1 right here. And these need to all be different. Don't just organize stuff here. So the main one we have to know is that sine squared of an angle plus cosine squared of an angle is equal to 1. Then we have to know how to manipulate this, and so we want to divide everything by one of these two trig functions. So I'm going to divide by sine squared. Okay, and make sure, by the way, you have the square. Don't forget the squares here. If I divide everything by sine squared, this becomes 1. This becomes cotangent squared, and 1 over sine squared is cosecant squared. Now I'm going to do that all with cosine squared. So sine squared over cosine squared, that would be tangent squared. Cosine squared divided by itself is 1, and then 1 over cosine squared is secant squared. And again, these lines are fill in the blank. They're not meant to look like fractions here. I could also ask you to move some stuff around. So once you have this, I could then say, hey, use this identity to find out what sine squared is equal to. And you would write that it's equal to 1 minus cosine squared. Or I could give you 1 minus cosine squared and ask you for sine squared. Okay? So you may have to add or you may have to subtract something over to the other side on this. All right, polar formulas. I'm going to ask a question like this. When converting from a polar coordinate to a rectangular coordinate, what formulas would we use? Well, you have to know polar is r and theta, rectangular is x and y. So we want to find what x is equal to and what y is equal to. All right, so that won't be written. You have to write that. And our formulas say that x is equal to r times the cosine of theta, and that y is equal to r times the sine of theta. And again, the way I remember this is I know I have these two, r and theta. I want these two, so I must solve for x and y using r and theta, cosine meaning x, sine meaning y. Going the opposite direction, from rectangular into polar, we need to solve for r and theta. So the way we solve for r is we use the Pythagorean theorem. So r squared is going to equal x squared plus y squared. Theta comes from the tangent function, so you could write tangent of theta equals y over x, but then we have to move it anyway and write it as inverse tangent, so I might as well start here. Inverse tangent of y over x. Or again, if the tangent was here and the y over x is there, that'd be fine as well. And then I don't know exactly how I'd phrase this yet, but you do need to know that whenever you calculate theta, if the coordinate point, the original rectangular coordinate point, was in quadrant 2 or 3, you have to add pi to whatever the calculator gives you. Now, if it's not in quadrant 2 or 3, you don't have to do that. You just, whatever it gives you is the actual angle, but you're going to have to add pi in these two quadrants. All right, sum and difference formulas. I don't write these as you know, some people do 4 separate. They do 1 for sine of a plus b, 1 for sine of a minus b. I just line it up so that the plus and minus goes with the plus and minus. And then for cosine, the plus or minus goes with the minus plus. Now, I will probably just have this first part, everything before the equal sign, written down, and you've got to write what they're equal to, okay? I might only have the minus, I might only have the plus, or I could have both. All right, so remember for sine, the order goes sine, cosine, cosine, sine. Okay, again, sine, cosine, cosine, sine. For cosine, the order is cosine, cosine, sine, sine, sine. All right, the first sign telling us to flip whatever this sign was. The angles are always going to be in the order A, B, A, B, A, B, A, B. So again, just so this is clear, you're going to be given whatever's to the left of the equal sign. It might have a plus or minus, or it might just have a plus, or it might just have a minus. And you're going to write sine, cosine, cosine, sine. This one stays the same right here. And then cosine, cosine, sine, sine, sine. Now, if we get these correct, we can use them to help us memorize the double angle formulas. So some people prefer just to memorize these and just kind of jot them down. I want to show you how to derive these based on our last formula. So what I'm going to do is I'm going to take, this is the sum and difference. I'm just getting rid of the minus, so I'm using the plus. And all the b's, there's a b here, here, and here, I'm going to change to a's. A. Okay, and the same thing here, A. Now, simplifying this top one, okay, we have sine of A, cosine of A, plus cosine of A, sine of A. Well, multiplying two things, cosine with sine, I could switch the order, so I could just flip it so it looks more like these. So let's do that. I'm going to just switch cosine of A and sine of A. Sine of A, cosine of A. Well, now I can see that my two terms, right, this term and this term, they're exactly the same. And whenever you add something to itself, it creates two of those things. And so what I could say is sine of A times cosine of A plus itself is 2 sine of A times cosine of A. And then on the left-hand side, I'm just saying A plus A is 2A. And so that's how I come up with this formula right here. 2 sine of A, cosine of A. With this one, same thing. This is going to become 2A. A plus A is 2A. 2A. Now I have cosine times cosine. Well, cosine times cosine is called cosine squared of A. Minus sine times sine is sine squared of A. And so this is our first double angle formula. Cosine squared minus sine squared. Minus sine squared. Now, to get the other two, we have to use our Pythagorean identity, which said that sine squared plus cosine squared is equal to 1. And so I am going to, and I would only do this while deriving formulas. I don't do this on actual problems, but I'm going to replace cosine squared with something and simplify. And then I'm going to replace sine squared with something and simplify that. So what can I replace cosine squared with? Well, I can make cosine squared equals 1 minus sine squared. Okay, so I'm going to replace cosine squared with 1 minus sine squared and see what happens. So 1 minus sine squared of A minus sine squared of A. Well, I'm subtracting negative sine squared from itself, right? Negative sine squared, negative sine squared. That gives me negative 2 sine squareds. So I'm going to take that 1, it's going to go right here. And I'm going to put minus 2 sine squared of A. Okay, so that's our second cosine formula. And now I'm going to do the same thing, but I'm going to do it with sine. So I'm going to replace sine squared with something, still using sine squared plus cosine squared equals 1. And I'm going to get sine squared by itself, 1 minus cosine squared. And now I'm going to replace this. However, be careful, there's a minus in front of it. So whatever I'm going to plug in needs to go in parentheses. I'm going to replace sine squared with 1 minus cosine squared. 1 minus cosine squared. And then I'm going to distribute the negative here to give me cosine squared minus 1 plus cosine squared. Again, both of these here get the negative. Well, now I've got 2 positive cosine squareds, and that's going to add to 2 cosine squared A, and we still have that minus 1. All right, so these are the double angle formulas. Some people prefer to, that this is too much, right? And they'd rather just memorize all of this here. That's fine. I find that more difficult than just deriving it. But it's up to the individual if you'd rather just memorize this, create flashcards, go through it like that, or if you want to walk through this process every time. All right, guys, that's it. Again, it's going to take some work, right? There's a lot of formulas here. And I do want to say, you're for sure going to get the double angle formulas, okay? You're for sure going to get the sum and difference formulas. You're for sure going to get all this polar stuff here. Everything else, you will get at least some of, right? You're going to get some of the Pythagorean identities, some of the logs and exponents, some of the unit circle stuff, all of this. But I may not ask everything on all these previous slides here again. The last last 2 slides, all right, all of this will for sure be asked on the test. All right, guys. Thanks for watching. Stay flawless.